Hello, everyone. My name is Shu Zhiyu from Duke University. Thank you for coming to my presentation of our paper, Unsupervised Flow Refinement Near Motion Boundaries. The optical flow of a point in the first frame is a 2D displacement vector pointing to the location of the same point in the second frame. As shown in the left example, the optical flow connects the location of the same point on a finger across two frames. A motion boundary is a curve on the flow field, across which the flow field is discontinuous. The right figure shows the motion boundaries on the motion field of the left example. Since the introduction of convolutional neural networks to the problem, the flow estimators have been achieving increasingly better performance on benchmark datasets. However, the maximum errors can still be very large, and many of them occur near motion boundaries. In general, the flow estimates worsen near motion boundaries. This figure shows plots of the errors of the flow estimates as a function of distance to motion boundaries on the Singtao dataset. Each plot represents the flow estimates of one flow estimator, including both state-of-art supervised and unsupervised flow estimators. As we can see, regardless of supervised or unsupervised setting, the flow estimates worsen near motion boundaries. The difference in accuracy of the flow estimates between 1 pixel and 20 pixels away from motion boundaries can be very large. There are several reasons why it is hard to estimate flow near motion boundaries. For example, it is typically assumed that motion is smooth spatially in flow estimators, either explicitly or inexplicitly. However, flow is discontinuous across motion boundaries. In addition, the features used for matching in these estimators are extracted from a large receptive field. For points near motion boundaries, those receptive fields would cross the motion boundaries, and therefore the features would be contaminated by different motions on the two sides of motion boundaries. Without flow labels for guidance during training, it is even harder to estimate flow accurately near motion boundaries under unsupervised setting. In this paper, we propose an unsupervised method that aims to first detect motion boundaries from initial flow estimates, and then refine these flow estimates near them. We show that the detected motion boundaries from these inaccurate flow estimates are helpful to improving the flow estimation near motion boundaries. Similar to the classical Canny edge detector, our proposed method uses hysteresis thresholding based on three binary feature maps. Motion discrepancy map is obtained by thresholding the magnitude of the gradient of the flow estimates. Edge map is obtained by an edge detector. We will explain the map of invalid smooth motion in details later. With all of these three binary feature maps, we classify every pixel in a frame into three classes. If a point is true in the motion discrepancy map, it is classified as a strong motion boundary point. For other points, if it is true on both the edge map and the map of invalid smooth motion, it is classified as a weak motion boundary point. The rest of the points are classified as non-motion boundary points. We upgrade a weak motion boundary point to be a strong motion boundary point if it is spatially connected to some strong motion boundary point. Now, let me explain our proposed map of invalid smooth motion. As the name suggests, the purpose of the map is to identify those boundaries whose two sides should not have similar motion. For point B on such boundary, we select two image patches on its two sides, patch A, the blue patch, and patch C, the red patch. Both patches have the same distance from the point B. Each of the patch has their own estimated motion, which is represented by the blue and the red arrow, respectively. The computation of the map is based on two observations. First, changes of appearance in the foreground and the background on the two sides of a motion boundary are more consistent with their own motion than the motion on the other side. That is, the blue patch is likely to have smaller matching cost if following the blue motion than following the red motion. The second observation is that the arrow of the estimated motion on one side can be much smaller than the arrow of the other side of a motion boundary. To illustrate, the figure on the right shows scatter plots of the endpoint arrows of all the AC pairs for the whole Singtao sequence, ILI2. Without loss of generality, suppose the error of patch A is smaller than that of patch C. The point clouds have long vertical tails in both the clean and the final passes. For instance, in this specific sequence in the clean pass, the error of flow estimates for more than half of the true motion boundary points is subpixel at A but not at C. Based on these two observations, we have the following conclusion. Suppose the motion near motion boundary point B is wrongly smooth, and suppose the flow estimate of the blue patch has smaller error. Then the cost of using the blue motion to match the blue patch should be smaller than using the blue motion to match the red patch. For points away from motion boundaries, where the motion should be smooth and the flow estimates are often accurate, the matching cost of using either motion should be small. Therefore, by distinguishing different patterns on the differences in the matching costs, we are able to identify those invalid smooth motion. We also found that adding the background motion improves the detection accuracy. An occluding motion boundary forward in time is a disoccluding motion boundary in reverse time. It is often that the flow estimates near these occlusions are more accurate than near occlusions. With better estimated flow on one side of the motion boundaries, the map of invalid smooth motion is also more accurate. Since the problem of detecting motion boundaries under unsupervised setting has attracted less attention, we can only compare with the baseline method that is based on thresholding the magnitude of flow gradients. We do the comparisons with input flows estimated by different flow estimators. From the table, we see that our proposed motion boundary detection method consistently outperforms the baseline method and is robust to different types of input flow estimates. This figure visualizes the three binary maps used in our proposed hysteresis thresholding method. In these two examples, our improvements are highlighted by the red circles. These false negative detections by the baseline method are identified by the map of invalid smooth motion on the fourth column, although the map can be noisy. Now, let's move to the second component of the proposed system, that is the flow refinement. Not all the flows near motion boundaries can be improved through the replacement method. There may not exist a good replacement flow nearby. There are two errors associated with the replacement process. One is the estimation error of the replacement flow. It tends to be increasingly smaller further away from the motion boundaries, as shown by the green plot in the figure. Another error is the approximation error. It comes from the fact that motion measured at 1 pixel replaces motion measured elsewhere. This error decreases as the replacement motion is taken closer to the replacement candidate, which is shown by the blue plot in the figure. In general, the replacement make improvements as the solid red plot is below the dashed red plot over a large range of distances. We observe that the difference in the flow values on the two sides of the motion boundary is a useful indicator of which points can benefit from replacement. When the flow estimates on the two sides are very different, the flow estimates on one side are likely to be affected by the flow estimates on the other side. For those motion boundaries, the side with smaller flow magnitude are more likely to be improved by replacement. At these points, the approximation error is smaller because the flow is smaller and therefore typically changes less rapidly. The estimation error is smaller as well because flow predictors do better on smaller motions. We need to first identify those points which are contained in set P as shown in the figure. The flow of those identified points are replaced by the flow of point Q away from the motion boundary, as shown in the figure. We evaluate our replacement method on the flow estimates by different unsupervised flow estimators, and on both the Sintel and the Kitty datasets. From the table, we see that our method successfully identifies those flows that can benefit from replacement. Some improvements on those replaced flow are very large. In this work, we propose a method that both detects motion boundaries and improves flow estimation near them under unsupervised setting. It exploits the fact that the error in taking flow estimates from some wrong point may be smaller than the error caused by proximity to a motion boundary. In other words, the smaller estimation error away from motion boundaries outperforms the approximation error in the replacement method. There are two main limitations of our method. The first one is that we only improve a portion of the flow near motion boundaries. In addition, the improvement is bounded. In future work, we aim to directly tackle the estimation errors of more points near motion boundaries.